Well, this week we made it through all three of Newton's laws. The first two were focused on this equation, the sum of the forces on an object equal the mass times the acceleration. We talked about the idea of inertia and how anything likes to retain its state of motion, whether it's at rest or whether it's moving, unless a force hits it, and when a force hits it, it changes its state of motion. It accelerates. That's law 1 and 2. Law 3 is the action-reaction. Right? You can't really push on something without having it push back. And that's actually a very deep idea. That really is what physics is. Physics is the study of the interactions between objects. And it actually tells you you never have an interaction just one way. It's always an action and a reaction. So that was really the focus, and we talked about the different kinds of forces. But now I want to point something else out. Let's see. We had this, and this is kind of where we defined mass. Mass is related to changing the inertia of something. So let's call that the inertial mass. But then we also brought in mass when we talked about the gravitational force. We said near the surface of the Earth, we have another force, we'll call it Fg, and it equals this mass times the acceleration of gravity, where this is a constant near the surface of the Earth. Now it comes from a universal constant. So when we get to talk about universal gravitation, we'll see that this is really just a combination of constants, including one that's a big G, constant everywhere, and the mass of the Earth and the radius of the Earth and everything. But still, this is just a constant acceleration. And what you might realize if you start to think about it is these are two different definitions of mass. This is the gravitational mass. And you might say they're the same thing. They look the same. F equals a mass times an acceleration. But they're actually physically completely different. This is how mass responds to a force. It gives it an acceleration. This is how mass responds to another mass. There's an interaction, and all interactions are forces. Right? So that's why they look the same in terms of the equations, because they're the same quantity. They have to, the units have to work out. That's why they look the same. But they're actually two very different definitions of mass. So the question you could ask is, do they have to be the same? Are they the same? Do they have to be the same? Well, they are the same. We measure them to be the same. The way we use them every day, they're absolutely the same. But it's a little strange to think about why. Why are they the same? So you can kind of look at it this way. You can say, here's a mass that's falling. Say this is Hal or Al, whoever it is. It feels a gravitational attraction to the Earth. So it feels Fg. That is just has to do with gravity. It has nothing to do with Newton's second law. That is just gravity. Feels that force. But then how fast does it fall? Then you apply Newton's second law. The sum of the, well, in this case there's just one force. So we'll just say Fg equals, and now Newton's second law, ma. Right? So they'll plug in for mg. It's the gravitational mass. That's the inertial mass, by the way. The gravitational mass times gravity constant equals the inertial mass times a. So you can say, how are these masses related? Well, you solve for a. You say this thing will fall at an acceleration equal to the gravitational mass over the inertial mass times this gravitational constant g, 9.8 meters per second squared. And when we experimentally observe that everything falls at g, that means this is always 1. The gravitational mass over the inertial mass, these two different things, are always the same. This is always 1. No matter how big the object is, it's always 1. If you ignore air resistance and all those other forces that might show up if you have other forces. If you ignore the other forces and just look at gravity, this number is always 1. So for some reason, gravitational mass and inertial mass, different properties of an object, have the exact same value. A little strange. So most of us would look at that and say, well, okay, let's move on with our lives. There's this guy named Albert Einstein. And Albert Einstein, he was a fairly smart guy. And he was always looking for the deep secrets of nature. And he said, this cannot be a coincidence. All right, so, well, okay, this is me making things up. But in my mind, he said, this cannot be a coincidence. There must be something deep here. And this is one of the many thought processes that led him to develop his theories of relativity. So let's look at the famous thought process he went to. He said, imagine an elevator, right? and two different situations with this elevator. In one of them, it's on the surface of the Earth. And you're standing in this elevator. So essentially, you're standing on the surface of the Earth, and you feel your normal weight pulling you down. You're used to that and everything. Now this elevator, let's say you're also in this elevator standing, and it's actually out in deep space. It's not near the Earth, it's not near anything that would create a gravitational force, but it's got a rocket thruster underneath it, right? So here, and it's shooting out flames, and this one is accelerating at 9.8 meters per second squared up. If you're riding in that elevator, accelerating up at 9.8 meters per second squared, you would feel a force. If the elevator is going to go at 9.8 meters per second squared, it's going to have to push you, and you're going to have to go at 9.8 meters per second squared. So it's going to take a force pushing you up that's going to be equal to force as mass times acceleration. It's going to take a force of your mass times your inertial mass times 9.8 meters per second squared, and that will feel just like gravity. Let's think also about this. If you were to take a ball and you were to throw it near the surface of the Earth, we've talked about the kinematics. It does something like that, right? If we're just sitting, we're in the lab frame, like here we are in the lab, we're in the lab frame watching this, we just see the standard trajectory. What about this situation? If you are in the elevator and you throw a ball up like that, what would we see in the lab frame? We would see, you threw the ball, you gave it an initial velocity, there's no gravity anywhere, there's nothing pulling it down, we would just see it go like this, right? But what would you see inside the elevator? Since you're accelerating up, you would see it go like this. You would see the exact same thing because it feels like there's a force pulling you down, okay? So this is getting a little bit into those inertial reference frames. So the dotted line is what we see in the inertial reference frame. This is what you see, is what you see, and what we now have is a non-inertial reference frame, right, because you're accelerating. So what Einstein, and this looks sort of cute, okay, that's how it is. But what Einstein said is, it's not just that it looks like the same thing, it's the same thing. He said, it's not just throwing a ball, it's light. If you shine light in this situation from the inertial reference frame, the light will go this way, straight across. If we're in the labs thing and you turn on the light and you're moving up, you just see the light beam going up. But if you're in the accelerating frame, you see the light beam kind of going down. Now, in gravity, you wouldn't expect that to happen because you're sitting in the inertial reference frame. The light should go straight. Einstein says no. A gravitational field is exactly the same as accelerating. The person in the elevator can't tell the difference. So in the elevator, on the Earth, the light should bend down. So it's not just throwing masses, it's things as fundamental as the propagation of light are affected by gravity as much as accelerating an inertial frame. That's why it's not a coincidence that these two are the same, they are the same. What Einstein basically then goes on to show is that there's no such thing as a gravitational force. It's really just things are following what they think is a straight line because mass curves space-time. The details of that are a little complicated, general relativity. But what I want you to see is even just from the very beginnings of looking at forces, there's already a little bit of a mystery you can understand that is heading towards very big ideas like general relativity.